Greetings students, welcome to Academic Coordinates. In this video we are looking at organic chemistry. Specifically we are looking at the reactions of nucleophilic addition to carbonyls, right? So initially nucleophiles are electron donors, right? And when we speak of carbonyls, we speak of this group right here where we've got a carbon that is double bonded to oxygen, right? So without any further ado, let's just dive right into it. So the reactions of nucleophilic addition to carbonyls occur mainly in two steps as far as mechanisms are concerned. So the first step is that the nucleophile is going to attack the carbonyl, right? And then secondly, we're going to have protonation of the anion, right? So as you might know, anion is a negative charge, right? So the nucleophile is going to attack the carbonyl, and then you're going to have an anion. You know, we might have an alkoxide there, and then protonation happens, right? So let's just look at an example right here. So let's say we've got a ketone. So this is a ketone functional group, right? And guys, functional groups are very much important. You cannot do reactions without mastering functional groups, right? So you've got our nucleophile there, an acidic proton. Okay, so let's just illustrate these two steps that I just wrote right here, right? And these are, guys, they are alkyl groups, right? So initially the nucleophile is going to attack the carbonyl right here at the carbon. Just take note before I go any further that the carbonyl group is like this, right? And so the carbon here is partially positive, and then the oxygen here is partially negative. Hence the nucleophile attacks here, right? And so when this happens, we are going to have an intermediate, right? Then there's our nucleophile there, and then we've got an intermediate here. So to just say this right here, that this is the first step. The nucleophile attacks the carbonyl, and there is the attack, right? And secondly, we're going to have protonation, right? So this negative charge is going to come here, and then we are going to have our final product, which is going to be like this. You've got our R prime right there. Then there's our nucleophile. Then we've got OH right there, which is an alcohol functional group, right? So looking at this, guys, let's just appreciate that the nucleophile attacked there at the carbon, then the pi bond broke, and then we had a tetrahedral intermediate, right, where it was protonated with this hydrogen right here, right? So let's just look at a real example now. Let's say we've got something like this, right? 1, 2, 3, 4. Okay, so let's say we've got something like this, and then here we are adding sodium cyanide, right? And then we've got an acidic proton right there, then water, right? And also, guys, remember, as I'm going through this, I will just emphasize basic things in organic chemistry which many might take for granted, right? So this is a ketone functional group, right? And so let's look at the longest chain. We've got how many carbons? 1, 2, 3, 4, right? So this is called 2-butanone, right? And then this ONE is the suffix for functional groups of ketones, right? And also just take note, guys, that we cannot start counting from this carbon right here. If you start counting from this carbon, we're going to be like 1, 2, 3, then we're going to have 3-butanone. However, when we are naming these compounds, right, we're going to start with the carbon that is closest to this carbonyl, right? Hence we said 2-butanone. You know what I'm saying? So this is carbon number 1, carbon number 2, carbon number 3, and carbon number 4, right? And if I can just put it on the side note there, that let's say we had something like this, for example, something like this. You know what I'm saying? So here, which carbon between this one and this one is closest to this carbonyl? It is definitely this one. So this is 1, 2, 3, 4, 5, 6, right? So this is going to be 6 carbons. So how we name this is going to be 3, 1, 2, 3, 4, 5, 6, 3-hexanone, right? So just take note that this carbonyl is on the 3rd carbon. However, if maybe this was the carbon that was closest to the carbonyl, then this was going to be our 1st carbon. Okay, let's get back to our work here. Okay, so here we've got this ketone, right? And this is the electrophile, and this now is the nucleophile, right? So how this reaction is going to happen is that the cyanide there is going to attack right here, and then the pi bond breaks, and then we're going to have a tetrahedral intermediate, right? We've got an O minus right there. Then there is our nucleophile, right? And then this is the 1st step. Then the 2nd step is protonation, right? Then we're going to protonate our anion right here, and then we get our final product, which is this, right? So there is our final product. So this is an example of nucleophilic addition to carbonyls, right? So I just want us now, guys, to appreciate, sorry about that, I just want us to appreciate something about these reactions, right? So let's go back a bit. So we had this right here, and then we had our alkyl groups, and then our nucleophile attacked, and then our pi bond broke there, and then we had this, right? We had this, and this is our nucleophile, and then O minus. Then eventually protonation happens, and then we had this. I want us to appreciate something about these reactions, or these separate steps, right? That this alkyl group and this one, the angle here is 120 degrees, right? And also this is sp2 hybridized, right? And so when the nucleophile attacks, we are going to have something like this. So this is going to be sp3 hybridized, right? So now I just want us to look at this transition, that we moved from here to a tetrahedral intermediate, right? So this was planar, and then this was a tetrahedral intermediate. So from sp2 to sp3, right? So it's quite important to realize what has happened here, because we're now going to speak about the reactivity of two important functional groups. And it's very much important for you to know the change here, right? In the sense that when the nucleophile attacks, this angle is going to decrease to about 109 degrees, right? So now, without wasting any more time, let us look at two most important functional group that has got a carbonyl in their structure, right? So we have aldehydes and ketones. As I've said, guys, that it's very much important for you guys to know your functional group, right? Functional group are quite important. They are actually the identity of a molecule, and if you do not know functional group, then you're going to struggle to do these reactions, right? So functional group, guys, are quite important. So aldehydes, they've got a carbonyl group, and then obviously this side it's a hydrogen. Okay, let's just have this one right here. And then a ketone, also they've got a carbonyl group. And then let's say we've got something like this, right? Then if I can name this is 1, 2, 3, right? So this is propanal, right? Then this one is 1, 2, 3, 4. But now the carbon that is closest to the carbonyl is this one. So we're going to have 1, 2, 3, 4 butanone. And guys, take note of the suffix there, right? This is how we name this functional group. If it's an aldehyde, it's going to end with this prefix. If it's a ketone, it's going to end with this prefix, right? So taking into account what we spoke about on the previous time when we were analyzing the transitions, right? In the sense that we move from sp2 to sp3, right? And then obviously the angles there, the bond angle, it decreases from 120 to about 109 degrees, right? So we are going to use this phenomenon when we're going to look at which one between these two is more reactive, all right? Okay, so let me just put it out there to you guys that between aldehydes and ketones, aldehydes are more reactive than ketones, right? So aldehydes are more reactive than ketones. So there are two reasons for this as to why aldehydes are more reactive than ketones. One of them is steric reasons, right, which we're going to look at now, and the other ones are electronic reasons, right? Okay, so basically let's look at why aldehydes are more reactive than ketones, right? Okay, so we have our carbonyl right here, and then hydrogen here, right? And then here we've got an alkyl group, and then maybe let's say we've got okay, let's say our molecules are like this, right? So just take note that this is hydrogen versus CH3, right? Just take note, guys, that here it's CH3, right? Okay, so now remember that this is sp2 hybridized, and then we're obviously gonna move to something which is sp3 hybridized, right? So aldehydes are more reactive because if a nucleophile, or when a nucleophile attacks here, right, then obviously this pi bond breaks. This angle is going to decrease. The angle is going to decrease, and when this angle decreases, right, this CH3 and this H are going to be brought closer to each other, right? And obviously even here, this CH3 and this CH3 will be brought closer to each other when the nucleophile attacks, right? So when the nucleophile attacks, the substituents here will be brought closer to each other, because obviously there is a reduction of the angle 120 degrees to 109 degrees, right? So when they are brought closer to each other, it is much more easier for hydrogen, which is very small, to be brought close to this alkyl group compared to this alkyl group and this alkyl group being brought close to each other. In other words, it is better for the small substituents and another substituent to be brought close to each other compared to this substituent, which is bigger than this one, to be brought close to each other. So in other words, this reaction will happen with ease. This will happen with great ease, right? And then obviously with a low energy compared to this one, right? And guys, especially when we have got bulky substituent, right? So let's say we had here maybe a substituent like this, right? So obviously when a nucleophile attacks and these are brought close to each other, it's going to be much more difficult compared to this. However, this still works also. This still explains it because of H is much more smaller than CH3. You know what I'm saying? So that is why now, guys, we say that aldehydes are much more reactive than ketones, you know. And then this is situations where we normally refer to as, you know, steric hindrance, right? As to maybe you might get a question as to why are aldehydes much more reactive than ketones. So that is your reasoning there, especially maybe if they say to you, just give reasons or steric factors that actually affect this reactivity. So that is how you're gonna look at it, right? Okay, guys. So next in this portion of the work we are doing, we are gonna look at important reactions, right? This is just an introduction to this, but you're gonna get more insight to it as we go further, right? So we are gonna look at nucleophiles, nucleophilic, right, attack, right, by a hydride, right? So obviously I use this hydride very loosely right here, but you're gonna see the reason I'm doing that, right? Okay, so basically let's say we have something like this. Let's say we have got you know, I love ketones. Let's say you've got a ketone like this, and then a hydride attacks eventually, and then after the workup we're gonna get a product of this nature, right? And this is called a reduction reactions, right? These are called reduction reactions, you know. And also, guys, if I can just go a bit to electrochemistry, you know, reduction reactions, or in reduction there is gain of electrons, right? And to just put it out there that this ketone was reduced, right? Reduction occurred, and then we had this alcohol right here, you know. And then here there are two bonds that are directly attached to a heteroatom, right? And here there is one. So now, guys, to actually accomplish reduction reactions, we need stuff called reduction reagents. And this is one of the most useful reduction reagents that are used. This guy right here. You're gonna see this guy, you know, almost everywhere you go, you know. So this is a reducing agent. It's called sodium borohydride, right? This is called sodium borohydride, and it has got this structure right here. So we've got the sodium ion, and then Then it's got 4 hydrogens right here. Then we've got a negative charge there. So this guy is a reducing agent, right? And if I can just give it away right now, that this guy is going to reduce only aldehydes and ketones, right? So when you've got other functional group, for example, like esters, the esters will not be affected, right? Okay, before I can say a lot of things, let me just demonstrate what I'm talking about right here, you know? Okay, so let's say we've got this right here, okay, and then maybe at home you might know what this structure is. This is called 1 2 3 4 5. So I started from this carbon because of it is closest to this. So this is 2-pentanone, right? Okay, so and then this is our reducing agent, right? So what is going to happen right here, guys, is that we've got our reducing agent right here, and then this is the electrophile, obviously. Then this is going to be the nucleophile. So guys, this reaction is quite important in terms of the mechanism, right? You might be tempted, since you are seeing a negative charge right here, you might be tempted to be like, okay, you know what, you know, my Kelly arrow is going to start from the negative charge to this, but that is not going to happen, right? So let me just get another color right there, you know. So how this reaction is going to happen is that this, from here, this Kelly arrow coming here, this is not going to happen. This is, it won't happen like that. You know what I'm saying? As you guys might know, that nucleophiles might have a negative charge, or nucleophiles might have a lone pair, right? So the arrow can start from a negative charge, you know, a lone pair, or from a bond, right? From a bond, you know. So in our case here, the Kelly arrow is going to start from the bond, right? So how this would happen is that it's going to happen in this way, right? So we've got our thing right here. Remember, this is nucleophilic attack by a hydride. So we're going to do our reaction like this. This is going to come here, then the pi bond breaks, and then okay, sorry about that, let me just lift up my page. Okay, so and then we're going to have our tetrahedral intermediate. So there is, let me just write it in green. This is the hydride that just came to join us right here, and then we have our O minus. Then after work up or protonation, let's say we had water there. Let me write it like this rather. So this is going to attack this hydrogen, and then we have our alcohol, right? We've got our H, then we've got our OH right here. So this is called a reduction reaction, right? So a hydride attacked, and then we had right there a reduction reaction, you know. And you know, sometimes we might call them there was a hydride transfer, you know what I'm saying? So basically, guys, I just want us to take note here that this guy, sodium borohydride, is one of the weak reducing agents. Sodium borohydride, this is one of the weak reducing agents, you know what I'm saying? So it's not going to reduce everything, right? But it is limited to ketones. Let's also do maybe a reaction for aldehydes so that you guys can appreciate this, you know what I'm saying? So let's say we had an aldehyde like this, right? So what is the name? 1 2 3 4. So this is butanal, right? So what is going to happen here, guys, is that, so there is our nucleophile, and it's important to know, guys, that here it is actually the hydrogen or the hydride that leaves, right? So you might see other mechanisms having curly arrows like this, right, to just show that this is the guy that is coming here, you know. Okay, so you will have our thing like this. So we've got O minus, and then we have our H there, right? Obviously we do have another H here, you know. Then after the work up and protonation, we will have, okay, let me up my page, we're gonna have OH right there, right? And let me just say it, guys, that you see this guy was reduced, you know what I'm saying? So this is a primary alcohol. This is a what? A secondary alcohol. And the reason I was able to determine that is because this OH group is attached to a carbon that is attached to two other carbons. This OH group is attached to a carbon that is only attached to one carbon. So this is a secondary alcohol and a primary alcohol. And now, is it safe for me to say that reduction reactions, so in other words, reduction reactions, ketones are reduced to form secondary alcohols. And then aldehydes, they form primary alcohols, right? So when reduction happens, you know what I'm saying? So ketones form secondary alcohols, and then aldehydes form primary alcohols. You know what I'm saying? So to just look here, guys, I just want you to see the power of sodium borohydride and its limitation, right? Okay, so let's say we've got this structure right here, and obviously this is a ketone, you know, right? So when we reduce this using sodium borohydride, sorry, right? And then let's say we've got an alcohol here, you know, this is going to be reduced to a secondary alcohol, right? This is a secondary alcohol, right? And let's say, for example, we also had something like this, I don't know, like this, you know, I'm just making things up here. Okay, something like this as well. And then sodium borohydride is our reducing agent. Then MEOH, still this will be the same. All right, secondary alcohol, you know. So now, guys, I just want to put something to you. Let's say now we have got something like this. Let's say you've got something like this. Then we've got this. All right. Okay. And then we use this, our sodium borohydride is our nucleophile. Then let's say you've got water here, right? Okay. Okay, cool. So basically this functional group is an ester functional group. Then this is a ketone. And remember, guys, that we said sodium borohydride can only reduce ketones and aldehydes. So the structure that is going to result here is going to be this. All right. Okay, then we've got our ester there acting like a boss, unchanged. You know what I'm saying? So that is quite important, guys, to know. You know what I'm saying? Sodium borohydride is one of the weakest reducing agents. You know what I'm saying? In the sense that it's not gonna affect like esters. You know what I'm saying? It's only going to affect ketones and aldehydes. So if you see an ester somewhere, you know, and then there is sodium borohydride, that ester is just gonna chill and relax and be like, you know what, I'm not going anywhere. All right. So okay, guys, we are almost done with nucleophilic addition to carbonyls. Let us look now at something also important, right? So let's look at the addition, right, of the organometallic reagents, right? So let's look here. So when we speak of organometallic reagents, so organometallic reagents, these are nucleophiles. And then you might be there at home being like, what in the world are you talking about when you say organometallic reagents, right? So we've got a carbon that is directly attached to a metal, right? You know what I'm saying? So we've got that bond right there, you know, and the metals that we use here might be lithium, right? Got lithium maybe attached to carbon. Then these will be organolithium, right? These will be like organolithium, and we also use magnesium. Then these are organomagnesium, right? Okay, and these ones, guys, these ones have got a special name. You know what I'm saying? We call these ones organomagnesium. We call them the Grignard reagents, right? Okay. So, okay, cool. So these ones, in this case, right here, so we have got an organolithium and an organomagnesium, right? So now, guys, these are very powerful nucleophiles, right? So when we are speaking of powerful nucleophiles, you are talking about nucleophiles like organometallic reagents. Those ones are powerful nucleophiles, right? Okay, and also I want us to take note, right? When organometallic reagents attack, right? When these guys attack, they are going to form two things, right? There's going to be an alcohol functional group, and also there is going to be a carbon bond, right? That is going to form. You know what I'm saying? So, and also let me just before we go any further, just since these are very powerful nucleophiles, so their reactions occur at very low temperatures, right? So their reactions occur, these reactions occur at low temperatures, right? So these reactions occur at low temperatures because these are quite powerful nucleophiles. So if you are given maybe a bunch of nucleophiles and they ask you which one is a stronger nucleophile right here, if you've got, organometallic, though that might be your choice, you know what I'm saying? Okay, so basically, let's say we've got a reaction here, right? So these organometallic reagents, let's say they're going to be added on ketones and aldehydes. Okay, sorry. Okay, cool. So let's say we've got this guy right here. You know what I'm saying? And then we've got, I don't know. Let's say we've got MELI, right? So this is an organolithium, right? And then we have something that is going to protonate. Let's say water, right? And then let's say the solvent that is used is THF. And also, guys, THF is a solvent, right? Maybe you might receive a question that says, I think it's one of those 1-mark questions, maybe in a test or a tutorial, where they might say, what is, okay, maybe 2-mark, they might say, write this in full or draw the thing. So THF is drawn like this. So there's 1, 2, 3, 4 carbons, right? And then it's called tetrahydrofuran, right? This is THF. Okay. And also, guys, there is one important thing. Okay, obviously this occurs at very low temperatures. Let's say minus 78 degrees Celsius, right? Okay, another important thing, guys, here is that this needs to occur in 2 separate steps. That is important. 2 steps. That is very much important, right? And I'm going to tell you why that is the case. You know, let's just see how will this thing happen. How will it happen? Okay, let me see if my page is fine there. Okay, so this thing will happen like this. Okay, so this is a ketone 1, 2, 3, 4, 5. So this is 2 pentanone, right? So MELI. So basically, this is our reaction. This is step number 1, right? And this must be separate steps, guys. You cannot have both water and the organolithium in the same step, right? So you must react it with the organometal, right? And then you're gonna have an anion right there, O minus, right? And then you have your Me right there, your Me. And then now, guys, this is the second step. The second step will be the protonation step. And then it's very much important that this happen in a separate step. You know, guys, that is so much important. You know, it's even much more important than the weather right now. You know, okay, and then we've got Me right there. And remember, guys, I said when organometallic reagents are added, or when that attack happens, you know, an alcohol, there's going to be an alcohol, there is it, and then a carbon-carbon bond. So this is the carbon, then there is another carbon bond. You know what I'm saying? Okay, let me now come to what I was shouting about. These reactions happen in 2 separate steps because organometallic reagents react rapidly with water or stuff that can that have got an acidic proton, right, with water or acidic protons, right? They react rapidly in the sense that if MELI is in the same step, let's say with water, for example, right? This guy is gonna destroy the organolithium right here. Instead, it's gonna form an alkane right here. It's gonna form an alkane, and this alkane, you know, most alkanes, that they are one of those stingy ones. As far as addition reactions are concerned, alkanes will be like, you know, peace, right? So so the whole purpose of organometallic reagents reacting with ketones or aldehydes has been abolished, because if this and this are on the same step, this is going to react rapidly with this, right, to form an alkane, and so the lithium is destroyed already. You know what I'm saying? This is also the same, guys, with Grignard reagents, right? That they cannot be on the same step. You know, so just take note of that. Maybe if they ask you, why do we have, like, you know, 2 separate steps, you just tell them that the organometallic reagents react rapidly with you know, with water or protons and stuff like that. You know, they can be protonated, right? So it is very much important that water is added in a separate step, right? Okay, so, and also if you can take note of THF right here, the solvents that we use also, let's see, the solvents that we use also, they are aprotic solvents, right? So aprotic solvents are solvents that do not have acidic protons, right? Because it might happen that this guy can be protonated here before it can even react to this, right? So please, guys, take note of that, right? All right, let me just react something, because I reacted here with a ketone. Let me now react with an aldehyde. You know, then we're gonna just wrap this up. Okay, let me just be funny here and throw this at you. And then we have them, I don't know, butyllithium, and then let's say we have got I don't know, THF again, let's say THF, right? Then we've got water there. First step, second step. So when these react, guys, it's gonna form this. Let me just, you know the mechanism. So it's gonna be OH and then this BU right here, you know? Okay, remember initially or before we just said that what did we say? Reduction reactions. In reduction reactions, there is a high rate transfer, right? So aldehydes will be primary alcohols and ketones will be secondary alcohols. However, now in organometallic reactions, you know, where an organometallic reagent is added, aldehydes will form secondary alcohol. As you can see here, that this is a secondary alcohol, and then ketones will form tertiary alcohol. Right? There is your ketone there. You see, this is a tertiary alcohol. So that's worth noting, guys. It's quite important for you to note that. You know what I'm saying? Yes, so these are organometallic reagents and they are quite powerful. You know what I'm saying? And also we are not limited to organolithium, but we also have organomagnesium, which we are going to speak about later on, or in the other video. We also have organomagnesium, right? So we've got organomagnesium reagents, right? Okay, so organomagnesium reagents, these ones, guys, actually, we can write them like this. This R is an alkyl group, right? For example, let me just write this. This is methane, name. And then if we deprive this methane of one of its hydrogens, we're going to have methyl, right? So this is what we mean when we say alkyl group. We're going to have methyl. You know what I'm saying? Okay, so this is going to be directly attached to magnesium and X. X is a what? A halogen, right? And in most cases, you know, we use we use bromine, we use chlorine and stuff like that. Okay, and also they react in the similar manner with organolithium reagents. You know what I'm saying? So they also form alcohols, and also they also form alcohols when they react with ketones or aldehydes, and also there's an addition of a carbon to carbon bond, right? And how you make them? Synthesis of Grignard reagents. I remember the first time I was exposed to Grignard reagents, I always call them Grignard. You know what I'm saying? So you can just imagine that it was late, eh? Okay, guys. So basically, so what happens here, in order for you to form Grignard reagent, so you need an alkyl halide, right? So that might be, for example, this is an alkyl, as I've already drawn to you guys, an alkyl halide. So let's say halide, halogen, let's say you've got, I don't know, bromine right here, right? And then what is this called? This is called bromomethane. Am I correct or am I correct? Okay, so to make Grignard reagents, you need alkyl halide, right? And you're gonna add magnesium tannins right into that. Then how this is gonna happen is that you're gonna have, it's gonna be like this. Then magnesium will be directly attached to the carbon right there. You know, this is how you make Grignard reagents, right? So it's an so it's like this R X, right? X is the halogen plus the magnesium tannins, and then this can happen in an ether, you know, in ether, and then you're gonna have this R-MgX, right? Now let me just write this one. So it's RX. So you've got your magnesium tannins there, depending in ether, and then you've got R-MgX, right? Okay, so this is the thing, guys. This is what happens. You know what I'm saying? If you had, let's say, BuBr, and then we are forming now a Grignard reagent. This is gonna be BuMgBr. You know what I'm saying? So this is your Grignard reagent. So if you can just do, you know, maybe an example there, but you're gonna appreciate these ones later, guys, as we do more of these. You know what I'm saying? So let's say you've got okay, let me just be funny and put these substituents here, right? So, and then you have the pH, R-MgBr. First step, very important, guys. First step. Secondly, you have water right there, or you've got an acidic proton. You know what I'm saying? Okay, so what's going to happen here? Let me just do the mechanism. So it's going to be like this. pH MgBr. So this is the first step. This is going to attack here, right? Or other, in other mechanisms might actually remove these things. It might go directly this, or it might go directly to this, to just show that it is that is actually coming to the electrophilic site, right? This is the first step. Then obviously you guys know that it's gonna form. Sorry about that. It's gonna form this guy. Then pH, and then okay. Then only then will you add water, right? Only then in this second step. Then this is protonation. This is the protonation step, right? Then you have your final product, OH. You don't really need to show the hydrogens. Oh, sorry, your pH also. So you can imagine the amount of strain that is in this molecule right here, because obviously pH. Okay, let me just draw it here. Just draw it here, right? It's gonna be this, right? Then you've got this OH, then you've got this, then you've got this. So you can just imagine, right? And also, guys, this is the same as organolithium in the sense that if these two are in the same step, if they're in the same step, what is going to happen is that pH MgBr will react with water and be protonated. It's going to be protonated, you know what I'm saying? So you're going to have something like this. And this means that the Grignard reagent is destroyed, right? And we don't want this. Hence, these must be in two separate steps. That is very much important, guys. Okay, so let's just wrap up with the last thing. Now we call these there is another functional group that we normally look at. It's called acetals, right? But in this video, because of it's just an introduction, we're going to look at hemiacetals, right? Hemiacetals. So an acetal functional group is like this. Okay, let's see, we've got whatever there. It's one carbon that is directly attached to two oxygens. Then we've got an alkyl group here, another alkyl group. This is an acetal, right? And however, for this video, we're going to look at hemiacetals, right? You've got an OR, an alkyl group there, and then an OH group, right? So now, this functional group is a hemiacetal, right? Okay, cool. So now, guys, how we form hemiacetals is quite interesting. You know, to form hemiacetals, okay, these are hemiacetals reactions. Hemiacetal reactions, right? Okay, so we're gonna react. In order for us to form hemiacetals, we're going to react an aldehyde and add there an alcohol, right? or we're going to react a ketone and add there an alcohol, right? Okay, so let's just do one. I think we have exhausted our time right here. Let's say we have got, okay, yeah, something like this. Okay, so let's say you've got this, then we are reacting this with an alcohol, let's say MEOH, right? Okay, so what is going to happen is that, okay, this, why did I complicate life for myself? Okay, so okay guys, okay, this is so cool in the sense that we have never had this kind of nucleophiles that attacks, from the lone pairs, right, where the arrows are coming from the lone pairs. So you've got O them that has got lone pairs, is attached to Me-methyl, and then we've got hydrogen right there. So it's going to attack in this way, and then the pi bond breaks, and then okay, no, what am I doing? Okay, I think it's this structure that I drew that is busy embarrassing me now. Okay, like this, then O, M, E, H. Then obviously this oxygen now will be positively charged, all right? And then, so what's going to happen is that this guy is going to be deprotonated, all right? Me, right, it's going to be deprotonated. Then this guy comes here, and then we are almost at our final product. Okay, then we have OMe. So OMe is fine now, it's living its best life. So remember, we just deprotonated something, HMe, right? So we deprotonated it, and then we're gonna protonate here now. You know what I'm saying? Okay, then our final product is this right here. OH, OMe, then this. So guys, this is a hemiacetal. Right? Now we speak of a hemiacetal. So what is important here, or to sort of help you guys in terms of the time you might spend, maybe when you receive questions, you might receive, for example, questions that show you the final structure, and they say to you, what were the initial, how can I put it? What was the initial structure? What were the initial reagents, for example? So how are you going to do that? For example, here, okay, let me use another color for that. Okay, we are wrapping up. So let's say you got this. This is what we have actually. 1, 2, OH, OMe. Okay, so from here, guys, then the question says, what reagents made this? What I want you guys to know is that where there is an OH, that is where there was a carbonyl, right? Don't be tempted to say it was this one. So obviously this is the chain 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So on this carbon, this is where the carbonyl was. You know what I'm saying? And then here where there is OR, remember this is R, the alkyl group, that is where the alcohol was. Remember, it's an aldehyde and alcohol. Sorry, here specifically for this one, it's a ketone and alcohol. If it was aldehyde, it was going to be this. OH, OMe, then there's going to be an H here. So where there's OH is where there was the carbonyl, right? And then the alcohol, you just take this OMe right here, and then you just put an H. So MEOH, right? Then here, the aldehyde, there's the carbonyl right there. Then you can put this H here if you want or not, which it's the same, right? MEOH. You know what I'm saying? Okay, so this is how we roll, guys. These are hemiacetals. So to form hemiacetals, we need ketones plus alcohol. So just take note of that, or aldehyde plus alcohol. Then you're gonna form hemiacetals from there. All right, guys. This was nucleophilic addition to the carbonyl group. So we've more or less covered some brief introductions on quite a number of things, right? So please go revise this at home. Make sure you understand it. If you've got questions, comment below or email me or call. No, not call. Email me. You know what I'm saying? Or send me an inbox on Instagram or TikTok or I don't know, Facebook, whatever, right? All right, guys, do stay blessed and enjoy the rest of your day.